Hello, good day, everybody. Yeah, once again, welcome to Chemistry 235 class, Basic Organic Chemistry. Today, we shall be looking at factors affecting the availability of electrons of organic compounds. As usual, I am your tutor, Mubarak Amin, and I'll be taking you through the class today. At the end of today's lesson, you should be able to identify the factors that affect the availability of electrons of organic compounds. We should also be able to discuss the factors that affect the availability of electrons of organic compounds. We should also be able to identify and also discuss the various applications of these factors that affect the availability of electrons of organic compounds. Before we go ahead, you will recall that in our previous discussion, we mentioned that if you have a molecule in which you have atoms of different electronegativity, the more electronegative atom will pull the body electron toward itself, thereby creating a polarity in the bond between that atom and the carbon atom. As a result, a reaction can easily take place. But in the case of hydrocarbon, compounds in which you have just carbon and hydrogen, carbon and hydrogen are of almost the same electronegativity. Therefore, there is no polarity in the bond between carbon and hydrogen, and no polarity between carbon and another carbon atom. We refer to such compound as being non-polar. As a result, if you have electrophiles and nucleophiles, they can easily react with molecules in which the bond is polarized. But the reaction with non-polar compound cannot take place so easily. Elements with higher electronegativity, such as oxygen and halides, can change the electron density around an organic molecule and make the molecule more reactive. This is known as electronic effects. These electronic effects have implications in the sense that they affect the chemical reaction of such molecule. They also play a role in stabilizing the molecule. They can make compound less volatile. They will also make a molecule more likely to react in a desired fashion. And also they affect acidity or basicity of molecules. If you understand the factors that are involved in this electronic imbalance, you can be able to understand the underlying mechanism of a chemical reaction. You can be able also to you can also be able to predict the product of such a reaction, and we can predict the behavior of organic molecules. The factors that affect reactions that affect electrons, availability of electrons, and in contrast, the reaction include inductive effect, electromeric effect, resonance effect, hyperconjugation, and steric effects. We shall start by discussing inductive effects. Inductive effect is a permanent state of polarization in a molecule. Permanent state of polarization in which the electron density in a bond between two unlike atoms is not uniform. For instance, if you take this structure here, you have carbon atom bonded to an electronegative atom, and you can see that carbon have partially positive, the atom is partially negative. This to show that the bond between the two atoms is polarized, with the bonding electron spending more time with the electronegative atom than carbon. If the electronegative atom is connected to a chain of carbon atoms, then the positive charge is relayed to the other carbon, as you have in this diagram. This is the carbon that is next to the electronegative atom. Then this one is the carbon 2 is next to carbon 1. You can see that as carbon 1 is partially positive, carbon 2 is also partially positive, and so on and so forth. The only thing is that the positivity reduces as you move from carbon 1 to carbon 2 and to carbon 3. This is what we call inductive effect. The effect of the pulling of electron by the electronegative atom X is felt along the chain, but the effect decreases as you move from carbon 1 to carbon 2 and to carbon 3. And in essence, the effect diminishes after carbon 3 or carbon 4. The inductive effect is a permanent effect, but it's weaker than and can easily be overshadowed by other electronic effects, which we are going to be discussing later. There are two types of inductive effect. You have the positive inductive effect and the negative inductive effect. Positive inductive effect is when you have an electron withdrawing electron withdrawing species attached to a carbon chain, which is drawing the electron toward itself. In such a situation, we have negative inductive effect. But in the case of positive inductive effect, we have an electron donating species, donating electron towards the chain of carbon atom. In such a situation, we say we have a positive inductive effect, or call it electron donating effect, as you have in this diagram. Here, X is an electron withdrawing effect, so it constitutes negative inductive effect, while Y is an electron donating species, so it exerts positive inductive effect. The relative inductive effects are measured with reference to hydrogen. Atoms or groups having greater electron affinity or electron attractive power than hydrogen are said to have negative inductive effect, whereas atoms or groups having lesser electron affinity than hydrogen are said to have positive inductive effect, as depicted in these examples. The positive inductive effect is observed among the less electronegative atoms of the molecule by electron releasing. Alkyl groups are usually considered electron releasing groups or electron donating groups. Other variants of inductive effect is the field effect. Field effect is similar to inductive effect in nature. However, field effect operate through space surrounding the molecule or through the solvent if the molecule is in solution molecule. So, whereas inductive effect, the original inductive effect is a polarization of bond between electronegative atom and carbon. Field effect operates through space. It's not necessarily a polarization. It operates through space. It is transferred through space. And when you have in a species in the solution, this will induce this type of effect. Another one is inductomeric effect. This is influence of inductive prior to a reaction by approach of a charged ion. Negative effect is enhanced by the approach of a negatively charged ion and vice versa. Inductomeric effect is a temporary effect. Applications of inductive effect. One of the applications of inductive effect is the bond lengths. Inductive effect affect the bond length of molecules. Let us use the halogens as an illustration. If you look at halogen, we have fluorine, chlorine, bromine, and iodine. We notice that the electronegativity of the halogens decreases as you go from fluorine through to iodine. In other words, fluorine is the most electronegative, while iodine is the least electronegative. If you now consider the bond between fluorine atom and the carbon atom, we notice that the bond between fluorine and carbon is shorter when compared to the bond between chlorine and carbon, which is in turn shorter than the bond between carbon and bromine, and the one between shorter than the one between carbon and iodine. Meaning that as you go from fluorine to iodine, the bond increases, the bond length increases. In other words, the stronger the inductive effect, the shorter the bond length. This is also depicted when the chain of carbon increases. The same effect is also experienced, in which the bond length decreases as you go from carbon fluorine bond to carbon iodine bond. Another effect of inductive effect is dipole moments. To illustrate this, we also use the halogens. Here we are using the molecule iodomethane, bromomethane, and chloromethane. We already know that chlorine among these three is the most electronegative and will exert the strongest inductive effect. And notice that the molecule which has chlorine atom has the highest dipole moment, while the molecule which has iodine, the least electronegative, the least inductive effect, has the lowest dipole moment. In other words, the stronger the inductive effect, the larger the dipole moment. Another application of inductive effect is the strength of acid. Inductive electron withdrawal increases acidity, and this can be illustrated with this list of acids. Here we have methanoic acid, this is ethanoic acid, propanoic acid, and butanoic acid. And the pKa of each of these acids is given. Generally, we know that the lower the pKa, the stronger the acid. The lower the pKa, the stronger the acid. As you can see here, the pKa increases as you move from methanoic acid to butanoic acid, meaning the acidity or the acid strength decreases as you go down. Meaning that as the number of carbon atoms increase, the acid strength of the acid decreases. This cannot be perfect because alkyl, the electron donating species, meaning they exert positive inductive effect. In other words, as the strength of the positive inductive effect increases, the acidity decreases. That is the summary of what you have here. On the other hand, when you have halogen, the acid substituted with halogen, for instance, we have ethanoic acid, which has a pKa of 4.76. Then we have iodoethanoic acid, bromoethanoic acid, chloroethanoic acid. And we notice that the pKa decreases, meaning that acid strength decreases. We already know that iodine is the least electronegative atom and we exert the least inductive effect. This is telling us that as the strength of the inductive effect increases, the acid strength also increases. That's what it means. Another illustration is what you have here. We have chloroethanoic acid. Then we have 2, sorry, 2,2-dichloroethanoic acid and 3,3,3 trichloroethanoic acid. We also notice that from chloroethanoic acid to 3,3,3 trichloroethanoic acid, the pKa also decreases rapidly, meaning that the acid strength also increases. In other words, as the number of electron withdrawing group increases, the acidity also increases. So we can conclude that the electron withdrawing species increase acidity of acid, and as the strength or the number of the electron withdrawing increases, the acid strength also increases. Another application is the strength of bases. Basicity is a measure of a compound's affinity for proton. And a convenient way to look at this is based on electron pair availability. The more available the electrons, the more readily they can be donated to form a new bond to the proton. And therefore, the stronger the base. Inductive effects also play a role in determining the acid strength of bases. Sorry, the basis strengths. This is illustrated in this example. Here we have ammonia, we have methylamine, we have dimethylamine, and trimethylamine. with their pKb given here. This is pKb, opposite of pKa, denoting the strength of bases. And as in the case of pKa, the lower the pKb, the stronger the base. You can see that ammonia here have 4.75 pKb, which is lower than that of methylamine, which is 3.34. This is not far-fetched because when you consider hydrogen, compare hydrogen with methyl here, methyl will donate more electron to the amino group than hydrogen, okay, thus increasing the basicity of methylamine. In other words, the more the electron donating species, the stronger the base. And this is also illustrated in the dimethylamine, in which we found out that the pKb is often lower than that of methylamine, 3.29. That means because we have two methyl groups donating more electron to the amino group, the basic strength increases. But in case of trimethylamine, we notice that the base strength decreases rapidly. This is not far-fetched. It's as a result of what we call steric hindrance. Because steric hindrance is operating here, it overshadows inductive effect. Thus, the basic strength decreases rapidly. We'll learn more about steric hindrance later in the course of our discussion. So, we can conclude at this point that inductive effect has many things to do in the bond length of molecules, the dipole moment, the acid strength, as well as the basic strength. Another factor influencing electronic availability of electron is what we call electromagnetic effect. Electromagnetic effect is an intramolecular movement of electrons from a pi bond to another atom in the molecule due to attack by a reagent. Electromagnetic effect is a temporary and reversible effect. There are two types, just like inductive effect. We have the positive electromagnetic effect, which is as a result of pi electron being transferred to an atom to which the reagent gets attached, as we have in this case. Here, the incoming proton is attached to this carbon, and the pi electron is also shifted to this carbon. This is what they call positive electromagnetic effect. And the negative electromagnetic effect is a situation in which the pi electron is shifted to an adjacent atom other than the one the attacking reagent is attached to. In this case, we have negative electromagnetic effect. Applications of electromagnetic effect is in addition reaction to alkenes. For instance, reactions of an alkene with bromine, addition of hydrogen halides to alkene, electrophilic addition reaction of alkene, and electrophilic substitution reactions of benzenoids. All these are applications of electromagnetic effect. Another one is addition to carbonyl compound. This is nucleophilic addition reaction. These are other applications of electromagnetic effect. We can compare inductive effect and electromagnetic effect. As such, they are similar but not the same. In inductive effect, the polarization of a single sigma, it forms sigma bond. When sigma bond is polarized, that's when you have inductive effect. But in the case of electromagnetic effect, it affects the pi electron in the molecule. When you transfer the pi electron from a bond to a particular atom, then you have electromagnetic effect. Inductive effect is a permanent effect. Electromagnetic effect is temporary. If the attacking reagent is no more there, the molecule reverts back to its original status. Inductive effect does not need an attacking the presence of any reagent because before it operates, whereas electromagnetic need an attacking reagent before it can operate. In an inductive effect, we have partial charges, partial positive or partial negative, whereas in electromagnetic fields, we have induced charges, +1 or -1, total charges, not partial. So these are the differences between inductive effect and electromagnetic effect. Now, resonance or mesmeric effect. Electron withdrawing or releasing effect attributed to substance through the localization of pi electrons, which can be visualized by drawing various canonical forms, is known as mesmeric or resonance effect. And the symbol for this is M for mesmeric or R for resonance. Also, resonance or mesmeric effect can either be negative or positive. Negative resonance or mesmeric effect is shown by substances or groups that withdraw electrons by the localization mechanism from rest of the molecule. If you have species that withdraw electron, it will operate negative mesmeric or resonance effect. The electron density or rest of the molecular entity is decreased due to this effect. For example, this species, nitro, carbonyl, and the rest, they exert negative mesmeric or resonance effect. In the case of positive mesmeric or resonance effect, the group shows positive mesmeric effect when they release electrons to the rest of the group, when they release electron. And a sample of species that will excite this type of effect are hydroxy, alkoxy, thiol, and so on. And this negative resonance effect or mesmeric effect is illustrated in this diagram. You can see the direction of the flow of the electron. In this situation, from the pi bond to the oxygen atom. In the carbonyl, now the carbonyl is withdrawing electron from the species. In this case, it's the cyano group that is withdrawing electron, and here it is the nitro that is operating the negative resonance or mesmeric effect. And here you have the illustration of the positive mesmeric or resonance effect. In this, the first one, you have hydroxy exerting this effect. And here we have amino group also operating positive mesmeric or resonance effect. In most of the cases, resonance effect is stronger and outweighs inductive effect. Application of resonance or mesmeric effect. This includes stability of carbocation. Okay, stability of carbanion as well as stability of free radicals. This application of resonance effect. As you can see in the example given here, here you have a carbocation on in this position, which is being, sorry, one moment, please, which is being stabilized by the pi electron. As you can see, the flow of the electron, and so on like that. Differences and similarities between mesmeric and resonance effects. Whereas mesmeric effect arises due to the substitution or functional group in a chemical compound. Due to substitution, sorry, due to substituents or functional group in a chemical compound. Resonance effect is as a result of the localization with which two or more structure can be written for true structure of a molecule, but none of them alone can explain all the properties of the molecule. It's called resonance effect. Mesmeric effect is a permanent effect which depends on the substituent or the functional group in the chemical compound. Resonance effect is also a permanent effect which refers to the localization of electrons in a given system. The group which show positive resonance effect also show positive mesmeric effect, and the group which shows negative resonance effect also show negative mesomeric effects. Hyperconjugation. Hyperconjugation effect is a permanent effect in which localization of sigma electrons of carbon-hydrogen bond of an alkyl group directly attached to an atom of the unsaturated system or an atom with an unshared p orbital takes place. For instance, in this illustration here, you have an alkyl group here, and you have a carbocation in which you have empty p orbital. The delocalization of electron in this orbital to the empty p orbital is what we refer to as hyperconjugation. Hyperconjugation involves the delocalization of sigma electron belonging to the carbon-hydrogen bond of the alkyl group attaching to an atom with an unshared p orbital. Hyperconjugation helps to explain the stability of alkyl radicals. The more the hyperconjugative hydrogen, the more the stability. As we can see in this figure, in this diagram. Here, this is tertiary carbocation, which is the most stable carbocation. And this is secondary carbocation, primary carbocation, and this methyl carbocation. Notice that tertiary carbocation is the most stable, while the methyl carbocation is the least stable. Because of the contribution of the electron in the alkyl group to the empty p orbital of the carbocation. Hyperconjugation, as you can see it. Then steric effects or steric hindrance. Steric effects are non-bonding interaction that influence the shape and reactivity of ions and molecules due to the size of atoms or groups. Steric effects have something to do with bonds, but the size of atoms, whether it is large or small, or group of atoms, okay, what we call bulky groups. Steric effects complement electronic effects, which dictate the shape and reactivity of molecules. Whereas electronic effects affect the properties of molecules, so also the steric effect. Common steric effects include steric hindrance and van der Waals repulsion. And steric effects we can illustrate with these two figures here. Here we have methanol, and here you have tertiary butanol. We can visualize the central carbon in each of these molecules. Here, the central carbon in methanol is bonded to 3 hydrogen atoms, whereas here it's bonded, this carbon here is bonded to 3 methyl groups, okay, and hydroxy. We can see that methyl group is larger when you compare to hydrogen. Okay, so we say that the carbon or the hydroxy in tetrabutanol are surrounded by bulky group, the alkyl groups. Whereas in methanol, they are surrounded with smaller group atom, which is hydrogen. This is what we call this alkyl group, methyl group around the carbon and hydroxy will constitute what we call steric effect. And by extension, they also constitute what we call steric hindrance because they prevent some reaction by steric hindrance. Another illustration is what we have here. Here you have ammonia, nitrogen atom bonded to 3 hydrogen atom. Then you have trimethylamine. If you remember when we were discussing the basic strength, okay, here the nitrogen are surrounded. The non-bonded electron surrounded by 3 hydrogen atoms, which are small atoms. Here, the non-bonded electrons here are surrounded by methyl. They are bulky groups. They will prevent the availability of the lone pair of electron. Here, the lone pair of electron will be readily available for reaction. And that is why ammonia will be more basic than trimethylamine because of steric hindrance or steric effect. In organic chemistry, steric effects are nearly universal and affect the rates and activation energies of most chemical reactions to varying degrees. So steric effects also have an effect in the availability of electrons. So far, we have discussed a lot about the factors that affect the availability of electrons in organic compounds. And in summary, what we have learned so far, we have learned that electron availability in a particular bond or at a particular atom in a molecule is a dominant factor which determines the reactivity of the compound. Saturated hydrocarbons are thus non-reactive because there is no polarity in carbon-carbon and or carbon-hydrogen bonds. Electronic effects are involved in chemical reactions, stability of a molecule, volatility of a compound, uh, reactivity of compounds, as well as acidity and basicity of compounds. Electronic factors that influence organic reaction include inductive effect, electromagnetic effect, resonance effect, hyperconjugation, and steric effect. Inductive effect is a permanent state of polarization and may be positive or negative inductive effect. Inductive effects affect the bond length, the dipole moment, the strength of acid, as well as the strength of bases of molecules. An electromagnetic effect is a temporary and reversible intramolecular movement of electron from a pi bond to another atom in the molecule due to the attack by a reagent. Electromagnetic effect may also be positive or negative. Electromagnetic effect is responsible for the addition reaction of alkenes, addition reaction to carbonyl compounds. Mesmeric or resonance effect is the electron withdrawing or releasing effect attributed to a substance through the localization of pi electrons. This can be visualized by drawing various canonical forms. Mesmeric or resonance effect may also be positive or negative. Mesmeric or resonance effect can be used to explain the stability of carbocation, the stability of carbanion, as well as stability of free radicals. Hyperconjugation is a permanent effect in which the localization of sigma electrons of carbon hydrogen bond of an alkyl group directly attached to an atom of the unsaturated system or to an atom with an unshared p orbital takes place. That is hyperconjugation. Hyperconjugation helps to explain the stability of alkyl radicals. Then steric effects are non-bonding interactions that influence the shape and reactivity of ions and molecules due to the size of atoms or groups. Steric effects are universal and affect the rate and activation energy of most chemical reactions to varying degrees. So far, we have discussed factors that affect the availability of electrons. And I believe you have learned a lot in this lesson. I will be hoping to meet you in our next class for more interesting topics. Thank you for your attention.